Assalamualaikum warahmatullahi wabarakatuh. My name is Kumar Madiha, and today for my paper review presentation, I will be reviewing an article written by Encik Ismail J. Mat Zin titled Subsidence Nature of a Strike-Slip Related Basin, an example learned from the Sarawak Basin. So first, we will begin with the background study. The Sarawak Basin was developed as a result of subduction of South China Sea oceanic crust beneath the northwest Sarawak continental crust. So there will be three basins in concern for the study. Firstly is the Rift Basin, which is the fast initial subsidence followed by slower terminal subsidence, followed by the Foreland Basin, which is the opposite, slower initial subsidence followed by rapid subsidence at the end of the basin formation, usually formed by lithospheric flexure by subduction. And last but not least is the Sarawak Basin, which is formed by strike-slip tectonism, early rapid subsidence followed by later phase where subsidence of the basement is slower. So it is similar to the West type basin. So first, we must understand the situation at that time. At the time, there were two seismic interpretations, which is the foreland and the strike-slip basin. So in the study, they will use the Basin Modeling System version 4 by Black River Associates, otherwise known as Basin Mod. So this study is to determine the tectonic subsidence history of Sarawak Basin using well data, and compare the profiles with foreland and lake basins. This is also to determine if the Mackenzie Basin model can be used for rifting and subsidence history of the Sarawak Basin. So in the methodology, there will be 9 wells selected from the Sarawak Basin, and they are labeled as such. And from these 9 wells, they will be looking into composite well logs and electric well logs. The composite well logs will include primary resistivities and curves, plus interpretation of the positional environment by stratigraphic data, big meter, and cycle boundaries. Geographic coordinates, spud date, water depth, fuel flow elevation, as well as the logical percentage, water depth, and the depositional environments are also obtained from the composite well logs, as well as the electric well logs. So the total depth is also incorporated, which also indicates that all the data below the true depth was not obtained from the well, but from the seismic or based on the information from nearby wells. So once the stratigraphy boundaries are set, the age of each sequence is determined using the stratigraphic chart, and the mean sea level is used as the beacon for depth measurement for all of the wells, which means that all the depth values for the top of each formation from composite well logs has been converted from depth to subsea depth. Furthermore, in regards to lithological percentage, there are three methods. First is the actual percentage of each lithology calculated from original wireline logs. And for those wells that don't have original wireline logs, an estimation was made using composite logs. And for some of the wells, which stratigraphic penetration is not deep enough to reach the basement, the lithological percentage beneath the maximum depth reached was estimated based on depositional environments of the sequences present above the basement using depositional environment maps for each of the sequences. Now, in regards to water depth and sea level. So the water depth for during deposition was estimated based on value depositional environments of sequence. During the study, they will use the maximum water depth is taken as the depositional depth of a particular sequence. As for the changes in the sea level, it is determined using the third order eustatic sea level curve of half Earth height, and the average between maximum and minimum sea is taken as the sea value for each sequence. And last but not least is the total and tectonic subsidence, which in the study will be used to display the 9 wells using the model software. So total subsidence is the combination of basement, otherwise known as tectonic subsidence and the subsidence due to sediment loading. So tectonic subsidence is the sinking of the crust on a large scale without any sediment loading. So we will be presented in a graph of burial history versus subsidence. So to determine the subsidence due to sediment loading, it is determined using isostatic backstripping. This method removes sediment layers, corrects for decompaction, fluctuation of sea level and sea depth, and assuming a isostasy, adjusts for isostatic rebound. So once we know the load-induced component of total subsidence, we also know the tectonic subsidence. Now moving into main outcomes. So for each of the wells, two curves will be displayed on the geohistory diagram, which is the tectonic subsidence curve and total subsidence curve. So there are terms to remember in the graph, which is SI, initial subsidence, STH, thermal subsidence or lead subsidence, ST, total subsidence, beta 1, the stretching factor from the initial subsidence, and beta 2, stretching factor from the thermal subsidence. So before looking into the results of the 9 wells, we first must identify the subsidence pattern for different basin types. So there are 3. Firstly is the foreland basin type, which shows the gradual decrease, and then the strike slip, which has a decrease and an increase, and lastly the Mackenzie type of basin, which shows a clear dip followed by a gradual thermal subsidence. So there it is labeled SI and STH. So here are the results for the first 4 wells: G411, D411, Nagai 1, and D22-1. So out of all these wells, it seems that G411 seems to show the most prominent subsidence pattern of Mackenzie Reef type basin, whereas the Naga 1 and D411 does not seem to show any signs of either a Mackenzie Reef type or foreland type, whereas the last one, D22-1, we seem to show strike slip pattern. Now these are the well results for the other 4 wells: Lucas F661, F14-1, and G51. So for Lucas and F661 and F14-1, these 3 show clear indication of a Mackenzie Reef type basin, whereas for G51-1 shows a pattern of neither of the basin types, but it could possibly be due to the strike slip pattern of the basin causes this pattern. And this is the result for the 9th well, P21. So like the previous wells, it doesn't seem to show indication of a Mackenzie Reef type or a foreland basin. So this might also be due to the strike slip formation that causes this type. So here is a quick summary of all the well results from before. So it shows that none of the 9 wells has a subsidence pattern that is characteristic of a foreland basin. So you see that none of the wells have a foreland basin subsidence pattern. Whereas for G4011, Glucose, F661, and F14-1 seem to show a Mackenzie Reef basin, whereas the rest, G4011, D22-1, G51-1, and G21-1, shows neither a foreland basin nor a Mackenzie Reef basin. Instead, these wells illustrate strong strike slip, but repetition of uplift and subsidence is not characteristic of a Mackenzie type Reef basin. And G2021 and G51-1 might show stronger strike slip patterns. Now, in terms of stretching factor, the stretching factor calculated for Sarawak Basin is high, the value of 3.16, compared to North Sea Dragon, which is 1.5 to 2.0, and Wessex Basin, Southern England, which is 14147, is considered very high. And these 2 basins that is being compared are actually rift type basins, with Wessex Basin being a strike slip type. So the closest So the closest stretching factor Sarawak Basin has is to the Patani Strait, which is in the Gulf of Thailand, ranging from 1.21 to 3.23. In the case of Sarawak Basin, the geothermal gradient is considered high as well as a stretching factor, but there is no volcanic activity due to the strike slip tectonic activity. Now we will look into what can be concluded from this study and also what are the recommendations that can be done to further improve this study. So overall, from the 9 wells, all of them have a subsidence profile which shows initial rapid subsidence followed by a slower and gradual thermal subsidence towards the end, and these phenomena resemble subsidence nature of both rifted and strike-slip tectonic origin. None of the wells show that the basin was formed as a typical foreland basin. Therefore, this basin is not a foreland basin. Furthermore, about the Sarawak Basin, the subsidence pattern is characterized by high rate of subsidence and high data values, plus local episodes of compression into speed with extension. However, some areas like J411 and D411, the subsidence pattern agrees with the Mackenzie-Wales model, and the evaluation of searching factors and heat flow for Sarawak Basin are consistent and match with the origin of a basin dominated by strike-slip tectonics. Therefore, we can conclude that the Sarawak Basin is formed by strike-slip tectonic activity. One recommendation that can be done is to have more geothermal gradient data, especially on the western part of the basin, since it was quite limited. So the relationship between the geothermal gradient and the stretching factor could not be determined on the western part of the Sarawak Basin. And to that, we reach the end and the conclusion of the paper review presentation regarding Sarawak strike slip basins. Thank you everyone, and Assalamualaikum warahmatullahi wabarakatuh.